Okay, this is a video on how to find the distance between parallel lines. Now, when we're finding the distance, we've already talked about how finding the distance between a point and a line, or the distance between anything, always has to be along a perpendicular segment. So all I've done is a very quick sketch of what these two lines might look like, and the only thing I really paid attention to was the y-intercepts. So this line has a y-intercept of 1, as indicated in the equation, whereas the bottom line has a y-intercept of -3. So that's the slope. I just kind of sketched it in. Okay, so the first thing is, where is this distance we're talking about? Now you can choose, I just need it to be from one point on one line to another point on the other line along a perpendicular segment. The easiest points to draw these distances from will be one of the y-intercept. You can choose either one. I'm going to choose the one on the line y equals 2x plus 1. So the distance that we're talking about will be something like this. So that's the length that I want to find. Now obviously, if I draw that length anywhere else between the two lines, it would be congruent. So we just need to start someplace. So what we want to do is, ultimately, our goal is to figure out the coordinates of this point right here, so I can then run the distance formula between 0, 1 and that point. So that's our goal. Now this is a lengthy process, so labeling your work is going to be really, really important in general and specifically to me. So I'm going to show you how I hope you'll lay this out, and this will take some space. The first thing I want you to do is I want you to find the equation of the line that contains the distance. So the equation of the line that has this pink segment in it, so we can think of it as extending in this direction. So two things that we know about that. We know that a point on that line would be 0, 1. And we know that the slope of the line is going to be perpendicular. The slope of the line is going to be perpendicular to the slope of our given lines. So we know that perpendicular slopes are opposite reciprocals of each other. So I know that the slope of the line that contains this distance would be -1/2, the opposite reciprocal of 2. This is actually a pretty easy formula. It's a nice thing that they have the same y-intercept. So I can say the equation of the line that contains the distance is y equals -1/2 x plus b, and I know the b because it's the same y-intercept as the first line. So y equals -1/2 x plus 1 is this line right here. So that's the first thing we're going to do. The second thing that we're going to do is we're going to figure out the intersection point. That pink point that I said was our goal. So the intersection point will always just be the solution to the system of equations. So the system of equations we're looking to solve is going to be the equation of the line that contains the distance that we just found and the line it intersects with, which is this 2x minus 3, this bottom line. By sketching the picture, I can see what line it intersects with. If I don't draw the picture, it's very easy to put the 2x plus 1 in that location. So give yourself the visual, it will really help. All right, so because these are both y equals, I'm going to go with substitution, even though it's not typically my method of choice, but I think this is set up best for that. I'm going to go ahead and clear my fraction by doubling everything. So I get that 5x equals 8. 8 equals 8/5, and I'm going to leave it as 8/5. I'm not going to change it to a decimal, I'm not going to change it to a mixed number, I'm just going to stick with 8/5. And then my y value that corresponds with that, I'm just going to sneak over the side because I know I have more work to do. So I'm going to say y equals 2 times 8/5 minus 3. So that's 16/5 minus 3, which would be 15/5. So I get that y equals 1/5. So the ordered pair right here is the point 8/5, comma 1/5. So we now have found the endpoints of the segment that we need to find the length of. So our last step is to actually find that length. Now there's some kind of technical work in here. The distance formula itself is not overly complicated, but how we're going to deal with it kind of can be. So I'm going to say that the distance is going to be the square root of x2 which I'm going to say is 8/5, minus x1, which is 0, squared, plus y2, which will be 1/5, corresponds, minus y1, which will be 1 squared. And I'm going to work in these fractions. So I have 8/5 squared, which is 64 over 25. Stick with it. It's going to work out in the end. Plus, this guy here is negative 4/5 quantity squared. So I have square root of 64 over 25 plus 16 over 25. And again, leave it in that format, trust me. Now, these guys both the same denominator, and that will happen. So I end up having a denominator of 25 and a numerator of 80. So if we think about our radical work, what we can do here is I can break a radical over division. And why this is nice is because this denominator is just going to reduce to 5. In my numerator, I have to simplify. So I'm kind of thinking off to the side, how do I simplify the square root of 80? So for me, I'm thinking that I think it's 16 and 5. So 4, 4, and 5. So my numerator is going to be 4 times the square root of 5 over 5. I can only interact regular integers with regular integers and radicals with radicals. So my final answer for my distance between these two parallel lines is 4 square root of 5 over 5. This is the process that I expect you to be able to illustrate. You will certainly be assessed on this. This is kind of a big idea from chapter 3. Which is a very short chapter. I'm looking to see that you can work with the fractions and that you can leave your answer in exact form, which means simplified radical form, no